Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. So here in this video lecture, we will discuss about the subject Digital System Design KC 302 as per the syllabus of Abdul Kalam Technical University, Lucknow. So here the topic we will discuss as TTL logic family from 4th unit. So the TTL gates are having the supply using as 5 volt. That there is a difference between the TTL logic family, or we can say the characteristics of the TTL logic family is the input and output voltage ranges are differed. That means we define a low voltage range and high voltage range for input and output separately. As let's say we are going to discuss this particular characteristics for this one. This one, the input range and the output range for TTL family. So we have the, let's say we are making the input window. This thing should be very clear before analyzing the TTL logic. And here we are having the output window. Okay. Now, one very important characteristics of this TTL logic family, the range for input and output is different. So here we are having the lower range for input. That means if the voltage level is below 0.8, okay, we will assume that the circuit will be at logic 0, right? And if the output voltage that is above 2 volts, then this is at logic 1. Okay, so between this the range is not determined. That means from 0.8 to 2 volt we are not able to differentiate between the logic 0 or the logic 0 is below 0.8 and logic 1 is above the 2 volts. So here this is not a distinguishable condition for any TTL family logic gate. So this must be very clear for the ranges for the input window, right? Similarly, if we talk of the output window in case of TTL logic, so here the input and output conditions we are going to be verify. The logic level 0 is defined below the 0.5 volts, right? So this is very, very important point. And the logic voltage is high, right? We assume that this logic is high for 27 volts up, right? So this is one major important point whenever we are going to discuss the TTL logic. This is one important aspect, and whenever we are solving the numericals or to identify which transistors and which diodes are in forward bias, or which transistor is on or it is off, then these ranges are very useful for that particular case. So here the most TTL circuit this having a similar structure, making of transistor logics only. Nand and AND gates are using as multiple emitter transistor or multiple diode junction inputs. Okay, so we will discuss one more important point here, that how the transistors are being seen whenever we are discussing the TTL logic circuit. So NOR and OR gates use separate input transistors and the PN junction. Okay, for PN junction, this is the TTL circuit operation will be based on whether the diode is forward biased or the diode is reverse biased. So most TTL circuits have some type of totem pole arrangements also. That means we are taking two transistors, separating them by using a diode, and this diode will make sure that one transistor is working and another transistor is off. If another transistor is on, then the first one will be off. So this is called as the totem pole arrangement that we are going to see. So here the input and output condition and the ranges we have already defined, that the above 2 volts is high for the input window, and 0.8 below will be considered as a logic 0. Yeah, and the high output window is above 2.7 volt and below 0.5 volts is the logic 0 for the output window. So this point is should be very clear. Now here another important part, this is an example of the transistor logic NAND gate. Okay, this is the transistor logic of a NAND gate. So here if we see, then we have multiple emitter transistor we are using in this circuit. So here this is a multiple input transistor. So as we have, this is a kind of NPN transistor, and the NPN transistor is having two inputs A and B, and these two inputs are going to the transistor Q1. The collector of this Q1 is connected to Q2, and here these Q3 and Q4 are known as totem pole. Here is a diode between Q3 and Q4, which is making sure that if this is on, this must be off, and if it is off, then this must be on, like this. Okay, so this is a totem pole arrangement, multiple input emitter, and this particular circuit is known as the TTL logic for the NAND gate. So here we can see we are giving a plus 5 volt supply. There are 3 resistances as a bias. You can see we have connected one more resistance also, and these are all biasing resistor and biasing arrangement for the given circuit. Now, every transistor in TTL logic that is viewed in the sense of diodes. Okay. So what we do is we are analyzing any transistor in terms of diode. This is very important. How? Let us see. Just a second. If I am talking of this is base, emitter, collector, and transistor, right? So how I am going to see this particular transistor? I will see this transistor in such a way. Okay, so this is the equivalent. This circuit can be viewed as two diodes that are connected in such a way. So here obviously this is base and this is my emitter and this one is the collector. Okay, so this is very important part whenever we are going to find out the state of the transistor, whether it is on or whether it is off, right? Now, so coming back to our NAND gate TTL logic, so we must understand what is the transistor equivalent of the this particular multiple emitter transistor, right? So here A, B are the two inputs given to the NAND gates, right? A and B are the two inputs which have been given to the NAND gate, and we will make the diode equivalent of the circuit. So here, see, this is my A. So what I did is, this is my NPN transistor, of course. So all these are written as like A as D2 diode I have made, and this input B I have made as a D3 diode, and this collector I have made as a D4 diode. So what I did is, this is my base, right? And I have made this AB, two emitter, EA and EB, and here collector. So EA I have made as a D2 and EB as D3, and this C collector as a D4 diode. So here this is the diode equivalent of the transistor Q1, right? Okay. I hope this particular part is clear. Then we can go to the next thing. So always try to make the the transistor into the diode logic. Once we have converted all the transistor into the equivalent diode, we are very clear with the operation. So next part from my side is, okay. So let's say we are going to analyze this one for any input. We will now change the input, and we will see how these Q1, Q2, Q3 and Q4 states are going to be, right? Let's say we give A as a 5 volt or 1, B as a 5 volt or 1. For the input window, whenever we are giving a plus 5 volt, the logic is 1. So we are giving 1, 1, both 1. For this one, the diode T2 will get off because this positive voltage is connected to this negative terminal of the diode, and here this B is also connected with the negative terminal of the D3 diode. So these two are cut off. So D2 is off, D3 is off. But see, what this positive is connected to the P terminal of this D4 diode, and hence I can say this D4 diode is forward bias. So whatever current is coming from this plus 5 volt, this is not going to flow in the A and B branches. Whatever current will come, that will go to the D4. That means to the base of the Q2 transistor. So when this current is going to the base of the Q2 transistor, it's very clear that the Q2 transistor is getting all the current. So it can operate very well, and hence the Q2 state will be on. Right. So whenever this Q2 is on, let us analyze what will coming out to be next. So Q2 is on in saturation. Q2 on in saturation. In TTL logic, whenever the transistor is on, it is in the saturation on. Okay. And this saturation will make this particular to be on. So if this is on, then this will be on. Okay. So here, because all the current which is going to here, this will also make this transistor to be on. And because this transistor is on, as I explained, this is a total pole arrangement. So Q3 will be off. So Q3 will be off. So what should be the next point? When Q3 is off and Q4 is on, then let us take the output from this X point. This is my output. This was input. Input is A, B, 1, 1. Now I want to find out the output. See, since this transistor is totally cut off from the side, so here no supply will be here. So this is connected to the ground, right? And here also the connection is lost, so it will be also a 0 volt. So 0 and 0, that will be equal to 0, and the voltage is very less. And for the output window, whenever I have already discussed that for the output window, the logic state will be 0 if the voltage is below 0.8 volts or 0.5 volts for the output window. So here the voltage is very less than 0.5 volt, and this particular X will be 0 in that case. So every time whenever we are analyzing this particular circuit in terms of TTL, transistor logic, we need to convert the transistor into its diode equivalent, and then we can easily by getting the diode to be on and off, we can get the circuit, how the functionality of the circuit in terms of the state of the transistors. All the transistors, we need to analyze all the transistor state. Here, like in this case, what we did is, according to the input A and B, we have analyzed this diode D2 and D3, and once we have found out that D2 and D3 is off, all the current is going through this through D4, making this Q2 as on, and whenever this Q2 is on, this saturation on is making this Q4 to be on. Okay, and if it is on, then obviously due to this diode D1, this Q3 gets off, and if this Q3 is off, then obviously the output here, we will find out the output, since this is grounded, and this from here it is not getting, this input is not getting any voltage, so there will be a very less drop between X and this point, X and ground. So ground will be X will be almost connected to the ground, and hence the logic output will be, of course, 0. Similarly, so here A and B are high, so Q3 is off. Okay. Next, let us verify one more case when A and B both are, both are off, or let's say one more case we will consider in this example. Let's say A is 1 and B is 0. Okay. So if A is 1, this is off, and B we have given as, this as 0. So here this no current will flow from this, but since this is on, all the current is going to be drawn from this one here. Why? Because this is having no, no resistance path. This G3 is short circuited. See, this is going to be a short because this is forward bias diode D3. So this, all the current will flow into this. No current will go here because this is off, and this is a high resistance path. Here it is also getting some resistance just because of this diode and the forward circuit. So this D4 is not going to be, current drawn. So if all the current is going through this B, or due to this short circuit which happened across T3, so this will make this Q2 to be off. This will make this Q2 to be off, and if this Q2 is off, this Q4 is also off, and if it is off, then this one is on, and whenever we are analyzing this voltage, like this is at plus 5 volt, this is conducting transistor, and some voltage would be there, and taking with this reference between these 2 points, the voltage drop will be high, as this diode, this transistor is conducting, and if this transistor is conducting, it is very clear that we are getting some voltage, and this voltage is above the output high range. So that I told you that the for this one the output voltage must be for output window greater than 2.7 volts. So this must be on, and hence we are getting some logic 1 into 0 and we are getting output as 1. This is again verifying the NAND gate. Now the characteristics of TTL. This is based on the bipolar transistors. We can make the diode equivalent of the TTL logic, one of the very most widely used families for all SSI and MSI applications. Operating voltage 5 volts, noise immunity between 1 to 1.6 volts, and they are optimized for speed power, and high versions are also comparable for CMOS. Now low power versions, they very less power they are consuming, at least per gate it is consuming only 1 milliwatt of power. So the power consumption is very low. So TTL logic characteristics are also being discussed, and I hope you must have got the output. One more thing that we need to practice about the numericals, and these numericals will be based on the input and output voltage ranges. But before that, you need to convert all the transistors into the diode logic, and by using that diode logic, you will just apply some network theorems that if the circuit is short, all the current will flow through the short circuit, no current will go to the resistive path. So these are some small concepts. Apply them, find out the condition of the transistor, and get the circuit analyzed completely, and hence the output. Thank you so much.